All right, let's talk about some boundaries and faults because you're going to need this information before we can do our project, which is coming up very soon. So you're going to need to know about how some plates interact with each other. We've already learned that the lithosphere is broken up into tectonic plates and they move relative to each other. Well, now we're going to spend some time looking at how they move and what happens when they do that. We get some landforms, and the crust of the Earth has different shapes now because plates move in some way. So you probably have this note page right here. This word is divergent. This is when two plates move opposite each other. So you would have a situation where there is one plate here and it moves this way, another plate moves that way. So they're moving opposite each other, they're moving apart from one another. So when two plates are moving apart from one another, that's what you would draw right here. Draw an example of a plate moving this way and a plate moving that way. Now in the real world, there are some examples that I'm going to try to show you here using Google Earth. So one example of a diverging plate boundary can actually be found, this is just one of many, but it can be found off the west coast here into the Pacific Ocean. And there is a small minor plate right here. It is called the Juan de Fuca plate. It's very small. The outline of it is a little bit right in here. Well, the other plate that it butts up next to is this big one that goes off this way, all this over here. This is the Pacific tectonic plate. Well, the Juan de Fuca plate right here is moving this way, and the Pacific plate is moving that way. So you can kind of zoom in a little bit and get an idea of why the ocean floor looks this way. It's because this plate all along here, this plate is moving that way, and this side of this plate is moving, of the Pacific, is moving that way. So Juan de Fuca plate here, Pacific plate right here, Pacific that way, Juan de Fuca that way. So diverging plate boundaries. So the next thing here that we want to look at is converging. When two or more plates crash into each other, lots of different things can happen. And because we have two different types of crust, we have oceanic and continental. So what does it look like when oceanic crust and continental crust converge? What does that look like? Well, there are some examples, and I don't want to get into too many of them right now because that's a part of your project, but oceanic to continental convergence, if I can rotate this, one of the things that kind of makes this a little bit annoying for me is the idea that every time you want to move the globe here, it changes its degree orientation, and I wish it would just kind of keep north the way it is. But here's a situation where you have one plate smash, and it's an oceanic plate, and it's smashing into the continental plate right here that's on the west coast of South America. And what you're getting here is the oceanic plate, which is more dense. It's plowing down and underneath this continental plate right here. So you get a very large trench system. This motion of the more dense plate plowing down underneath the less dense plate is called subduction. And whenever you get subduction, you're always going to get a trench first, and then later on, far away from the subduction, you're going to find mountain ranges most of the time. And all the time you'll find mountain ranges. But some of the time you'll even find these being volcanic in nature. So that is oceanic to continental convergence. The next one is oceanic to oceanic convergence. So let's take a look at what that looks like in real life. Let me zoom back out of here, zip around the world a little bit. Let's go a little faster, please. Here we go. Okay, here is an example of oceanic to oceanic convergence. You have the Pacific plate here, and it's actually slamming into a part of the Philippine plate, which is over here. The Philippine plate is kind of this one here. It's got a couple small minor plates in here as well, but if you kind of took this as the whole and called it the Philippine Plate, I'm not really going to argue at this stage of our understanding. But the Pacific Plate is slamming into this Oceanic Philippine Plate. So you're still getting subduction. The Pacific Plate is colliding and then subducting under the Philippine Plate. So you have a big trench, and then you start to get these underwater mountain ranges that eventually, through geologic time, will grow big enough to punch through the ocean surface, and you'll have islands and more land here eventually. So the last one is continental to continental. Where can we find an example of continental to continental convergence? And the last one, of course I picked the long way, but that's all right. The last one, and this is the most famous, and this may help you later in the project, but if you've ever heard India called the subcontinent of India, it's because at one time this was its own separate continent, kind of like Australia. Australia is its own continent. Well, India used to be the same. A long time ago, India was down here and slowly moved up and plowed into Southeast Asia. Well, they, of course, today are connected and converging. So India is plowing into Southeast Asia. So what you get is you get land slamming into land, and you get a trench here, but it's not nearly as large as the trenches in the ocean. But you immediately get mountains being buckled and pushed up. So all of these mountains here are made because this is slamming into that. So you've got the India plate slamming into the Eurasian plate. All right, the last one that we're going to look at for plate boundaries is transform. So here, plates can move apart from each other, spread apart. Here, these are examples of plates smashing into each other. Well, in this case, neither plate wins or loses. In other words, one doesn't get smashed up and over another, or one doesn't dive down underneath one. You get two plates that are sliding and grinding past each other. So they're going in different directions and they're sliding past one another. What does that look like in the real world? Well, there is a location right here in South China. Let's see if I can pencil it. Here we go. It's actually right in here. This is called the Red River Fault, and it is in South China, and it's also in northern Vietnam, right in this area. And what's happening is this part of the plate right here is moving this way, while this part of the other side of the plate is moving this way. So they're sliding past one another. No one's really winning or losing as far as getting a height advantage. This one's sliding this way, that one is sliding that way. And let's see if we can find some features here that would let us know that it's being that it's sliding past each other. I really can't see any obvious details at this height. I mean, if I zoomed in a lot more, maybe we could see some streets or something being moved about. But this is just one example of a transform boundary on the planet. This area moving this way, the other side is moving that way, and they're sliding or grinding past. Now, there's some faults information on here that you'll need to know. On the note page, normal, reverse, and strike-slip faults. We'll go over those in class in greater detail, but the last thing I want to mention here is at the very bottom. It's called a hotspot. As you'll note here on Google Earth, lots of things happen at the boundaries of plates. So the Pacific plate is on this side and the Philippine plate is on this side. And you're going to get mountains and islands and things at the boundaries where these plates tend to move. But there are sometimes things that happen just out in the middle of plates, around no boundary, and something kind of pops through the middle. There is actually, I was going to show you a different hotspot, but I think I've decided on another one right here. There is a hotspot underneath Yellowstone National Park. There's a hotspot under there. You can't really see it in great detail here, though. However, the most famous hotspot in the world, from the North American perspective, is Hawaii. If you'll notice, there are islands that are just kind of out in the middle of nowhere. There is no plate boundary. there's no edge here. This is out in the middle of the Pacific Ocean. So there are really, on the surface, there's no real tectonic reason for these being here, until we discover that the reason these islands exist, and they are all volcanic in nature, or they were volcanic in nature, what's happening is there's a plume of magma that's punching up through the crust, and it continuously erupts. And it erupts until you get land that punches through the top of the ocean. The volcanoes continue to erupt, and you get little islands. As long as these volcanoes continue to erupt, you're building landmass. And then as the plate moves away, the magma plume under the lithosphere stays right where it is. So once this island slides this way, there's actually going to be, in the future, there'll be a new island right here in Hawaii because the hotspot's located right here. And as you progressively move away from the hotspot, notice how the islands get smaller and smaller until the sea reclaims these islands. All of these are old Hawaiian islands that have been reclaimed. And then they even move this way up through the Emperor Seamount. All of these are old Hawaiian islands as well. So at one point the Pacific Plate was moving in a northern direction, and over the last several 100 million years the Pacific Plate has been sliding to the northwest. And so now you have present-day Hawaii, but that hot spot is it's already sliding off the east coast of the main island, and there's already a new island that's being built through volcanic activity. So this island is slowly turning off its volcanic activity, and there's a new island that's going to be built right here. And these are things that are punching through the plate. They're not located at a boundary, so in our notes we call those hotspots. All right, that's a very quick look of all of the boundary type information you're going to need to know so that you can be set free to start your project, and it's going to be called Geology on the Go. So, good luck.